Assalamualaikum and good afternoon, students. So today we continue our lectures through online system because of COVID-19. So we continue with page 23, chapter 3, testing standards. So all PV manufacturers test their product based on standard test condition, STC, which defined as follow. So the irradiance of normal incident is 1000 watt per meter squared, which is the symbol is G. The cell temperature is 25 degrees Celsius and the solar spectrum AMS 1.5. So all the manufacturer will do this STC at the factory. So all the values from the data sheet come from the STC test, or standard test condition. However, some manufacturers also declare a nominal operating cell temperature (NOCT). This is because NOCT seems more practical indication of the probable operating temperature in real condition. Because for STC, we can't have this 25 degrees Celsius at solar irradiance 1000 watt per meter squared for the real operating condition. So they make another test we call NOCT, which is at irradiance 800 watt per meter squared and ambient temperature 20 degrees Celsius, solar spectrum AMS 1.5 and wind speed 1 meter per second. So for Malaysia, our ambient temperature is between 25 to 28 degrees Celsius. So this NOCT compared in Malaysia climate is more acceptable compared to STC. Okay, number 8, factor that affecting the power output. So the actual output power produced from a PV module exposed under actual climate condition depends on light-induced degradation. So this is the losses, the type of losses that we call light-induced degradation, LID. So it will affecting the output power. So this LID is a loss of performance arising in the very first hours of exposure to the sun, usually with the crystalline PV module. So this LID will indeed represent a loss with respect to this STC, standard test condition. So this LID loss is related to the quality of wafer manufacturing. Okay? So the quality of this wafer manufacturing of the solar cells. So the LID loss is related to the quality of the wafer manufacturing, and maybe the losses is within 1% to 3% or even more. So another factor that affecting the power output we call potential induced degradation, PID. So this PID can occur when the voltage, potential and leakage current from the PV module drive ion mobility within the module and the semiconductor material or other element of the module. So there will be a leakage current through the glasses, mount and frame of the PV module. So this PID will reduce both module maximum power point MPP and its open circuit voltage along with a reduction of shunt resistance. So to avoid this leakage current through the frames, to the glasses, so what we can do is the easiest way is to avoid PID damage to the panel by choose a solar panel who via manufacturing quality has inbuilt PID resistance. So example here, let's see example. So this is example for one of the company in China, which is they introduced these PID modules. However, this PID module must work with the Huawei inverter, smart logger, PID inductor for short, and the other device. Okay, but we can use any other type of PV module, but we must install with this equipment, okay, from Huawei. Another method is we choose PV module with anti-PID characteristic. For example here from Jinko Solar. So this Jinko Solar is the first PV module manufacturer in the industry that guarantee anti-PID using this standard test, which is IEC 62804 test, which is include a 96-hour potential induced degradation resistance test under the condition of 85 degrees Celsius and 85% relative humidity at voltage plus minus 1000 volt. Then it produces a degradation of power which is less than 5%. Okay, so let's go back to the notes. Okay, another factor that affecting the power output is crack or micro cracks. So it might happen during manufacturing, transportation, or construction. So example in this picture, we can see the micro crack. So we have used a special equipment to see this micro crack. So snail trail, let's see this picture. So this is the snail trails on the PV module surface. So these snail trails are decoloration of the panels, which usually build up over a couple of years of power production on the field. So this moisture, the moisture from the surrounding, the installation surrounding, can enter through the back sheet and diffuse to the cell surface. So how we know that this snail trail will affect the performance of the module? What we can do is we can make several tests. For example, we use thermal imaging, okay, to see the condition of the PV module, or electroluminescence or IV test. Okay. The test is similar to this micro crack condition. So faulty bypass diode, short circuit or open circuit. So faulty bypass diode, we can replace the diode. Okay. Manufacturing quality, so the soldering of the grid. So example here, the quality of the soldering. Okay. Faulty soldering here. Solar irradiance also will affect the power output. This is a during performance, for example, because of shading or soiling because of dust or scratch glass surface, the tip angle of the PV modules, and the orientation, whether with a wrong orientation. So in Malaysia, usually we use PV module orientation which is facing south. So another factor that affecting the power output is the module temperature, which is depends on the air ventilation under the module. So under Malaysia climate, usually we propose for the solar pump, the gap between PV module, which is for freestanding PV module, is between 10 to 20 millimeter. So power tolerance depends on the PV manufacturing. So example here in this data sheet, let's see, do we have this any power tolerance? So example in here is between 0% to plus 10%. This is the HIT, HIT PV modules. Do we have another example here? So another example is from PV module monocrystalline, which is power tolerant plus 5% minus 0%. Okay, so the power tolerant increase 5% from the rated power. Okay, let's go back. So another factor that affecting the power output is the aging, which is degradation over time as specified by PV manufacturer. So for conventional PV modules, usually we declare that 1 year it will reduce 1%. Okay? Let's say the PV module already installed in 7 years. So 1 year, 1%. So after 7 years, the performance, the aging will become 0.93. Okay? So the performance is 93%. So the effect of module temperature on its output. So this module temperature or cell temperature will give a marginally effect on the current. So when the temperature increase, the cell temperature increase, the current will increase. But opposite with the voltage and power, this module temperature will give a significant impact on the voltage and power, which is when the temperature increase, voltage and power will drastically decrease. So it's very important to have this mounting structure that will give effect on the air ventilation under the PV module. So less air circulation could increase the module temperature. So what about solar irradiance? So the effect of solar irradiance on its output. So when the solar irradiance increase, it will give a linear effect on current and power. But for voltage, there is a marginal effect, which means that the voltage is almost constant, okay, even though the solar irradiance increase. So aging factor. So we assume in general the derivative factor is about 1% per annum. So every PV module power degrade due to aging. However, the important thing is you must refer to the PV manufacturer for actual derating factor. For example here, this SunPower, the company in US, the SunPower X series of PV module, they declared that on the first year of operation, the production of power will increase 9%. After 25 years, the PV module still produce 30% more compared to the conventional. This is the conventional PV module. So during the first year, the performance 100%. After 25 years, it goes below than 80%. So another example here for SunPower X series. Okay, example here. So here example of the SunPower X series. So the first year of installation, it will produce more than 150% 50% of energy production per roof, and after 25 years, 60% more energy produced. Okay? Compared to the conventional panel, which is 100% for the first year, after 25 years, you will go to 75%. But for this PV module, it will go up to still above 100%. So it produces more energy over 25 years. So another example, due to the manufacturing defect, which is interrupted contact finger of the solar cells, broken cells, and the dirty PV module. So example here is the crack during installation. Okay. So how to predict this voltage, current, and power of PV modules? So all electrical parameters given in the PV datasheet are tested under STC, standard test condition. Means the solar irradiance 1000 watt per meter squared, and the cell temperature is 25 degrees Celsius at AMS AM 1.5. So it will be different if the PV module operate under real operating condition, ROC. So the voltage drop as the temperature increase as equated below. So this is how you calculate or predict the output power under real operating condition. So VOC predict or VOC ROC, same thing, equals to VOC STC multiply with the temperature factor. So this is the equation of temperature factor of open circuit voltage. So VOC STC multiply with 1 plus gamma VOC in percentage. So we need to divide with 100. Multiply with module temperature minus STC temperature, which is 25 degrees Celsius. So to predict the voltage at maximum power or real operating condition of voltage at maximum power equals to VMP STC, same thing, VMP STC multiply with temperature factor for VMP, which is 1 plus gamma VNP. This is in percentage, so we divide with 100, multiply with module temperature minus TSTC, which is 25 degrees Celsius. So how to calculate this short circuit current? Okay, please remember that the characteristic of the short circuit current, which is when the solar irradiance increase, so the short circuit current will increase. So ISC predict equals to ISC STC multiply with all these losses. So we have 3 losses here, which is solar fraction, KF. So solar fraction equals to G. G is the value of solar irradiance during the operation, for example, 800 watt per meter squared. Divide with GSTC is the solar irradiance during standard test condition, which is 1000 watt per meter squared. Multiply with K dirt. K dirt is the losses due to dirt, which is standard we use 0.97. Multiply with mismatch factor for current. So usually mismatch factor of current is not given in the datasheet, so we assume 1. So why in this equation we don't have this temperature factor? Okay. If you compare to this equation, power generated by PV module, PMP predict equals to P array STC multiply with same losses KF, KF, K dirt, and mismatch factor for the power. But we don't have this temperature factor. This is because when the temperature increases, it doesn't give a significant impact on the current. Okay, remember back the graph. Okay, when the temperature increases, so it will give a marginal effect on the current. So that's why we don't include the temperature factor in the equation. But for power, we have this temperature factor because when the temperature increases, it will give a significant impact on the power, which is when temperature increases, the power will decrease. So K temp, so temperature, power, P represent power, is 1 plus gamma PNP over 100 multiplied with Tm minus TSTC. So KMM is the module mismatch. So for power, you need to refer to the power tolerance. Okay, where is power tolerance? So power tolerance, for example here, plus 5%. So KMM will be plus 5%, which is 105%. So 105% which is 1.05. So gamma PNP represent the temperature coefficient for power, usually given in percentage over degree Celsius or percentage over Kelvin, degree Kelvin. So example here in this data sheet, let's see the data sheet for temperature coefficient. Example here, temperature coefficient Pmax minus 0.30% per degree Celsius. This minus represent that when the temperature increase, the power will drop 0.30% every 1 degree Celsius. And also for voltage, temperature coefficient, remember back the graph, when the temperature increase, the voltage will reduce 0.126 volt every 1 degree Celsius. But different with current when the temperature increase, so that's why there is no negative polarity. When the temperature increase, current will increase 1.76 milliampere for every 1 degree Celsius increment. So how to convert this value into the percentage? Example here, what you need to do is minus 0.126 volt, you divide with open circuit voltage, which is 52.4 volt, and you multiply with 100 because in percentage, and then you will get the value for temperature coefficient in percentage. For temperature coefficient for short circuit current, to get the value in percentage, so 1.76 milliampere you divide with short circuit current, which is 5.85 ampere, multiply with 100 because you need a unit in percentage. So and then you can use this equation. Okay, you can use this equation to get the VOC predict or VNP predict, and also PNP predict. So a typical datasheet of a commercial module comprises the following electrical values at standard test condition. So again, STC at G1000, cell temperature 25 degrees Celsius, AMS 1.5. So all these values are given in the datasheet. Rated peak power, guaranteed power, short circuit current, open circuit voltage, current at maximum power, voltage at maximum power, efficiency, temperature coefficient. So we have three usually. Temperature coefficient for open circuit voltage, temperature coefficient for power at maximum point, and temperature coefficient at short circuit, and maximum series fuse rating. So this is a sample of the datasheet of commercial module as shown below. So we have nominal power. So this is the power tolerant, plus 5 minus 3%. So under worst condition, we take minus 3%. So your KMM for power will become 0.97. Rated voltage, VMPP. So voltage at maximum power point, 40 volt. Rated current, IMP, 5.25 ampere. Open circuit voltage, VOC. Short circuit current, ISC. And the maximum system voltage, IEC, which is 1000 volt. So temperature coefficient usually given 3, power, open circuit voltage, and short circuit currents. Again, you need to convert this one into percentage. So normal operating condition, NOCT. So this is tested under solar irradiance, 800 watt per meter squared, and the ambient temperature 20 degrees Celsius. So this NOCT, they declare 45 degrees Celsius plus or minus 2 degrees Celsius. This is the series fuse rating of the module, and the limit reverse current for 3 string is 14.4 ampere. So all this value is declared under standard test condition, which is solar irradiance 1000, MS 1.5, and the cell temperature 25 degrees Celsius. So the warranties is 25 years, limited power warranties, and 10 years limited product warranties. Okay, so we have two warranty, power and product. So this is the certification for this module, which is IEC 61215, edition 2, or and IEC 61730, SCII. So here is the size of the module, including the frame. So this is the width of the module and the length of the module. Usually this value is given in millimeter. So this is 1559 millimeter, and here is 798 millimeter. So it is very important to know that the temperature coefficient usually represented in the symbol of gamma. And also please bear in mind that all temperature coefficients are negative except for current. Okay, negative because the effect of temperature, when the temperature increase, it will give a significant impact on the power and voltage. Opposite with current, so when the temperature increase, current will increase. If percentage gamma VMP is not given, then you can assume percentage gamma VMP equals to percentage gamma VMP. This is because of the temperature coefficient. Okay, temperature factor, the characteristic for temperature vector for voltage and power is similar because the powers come from the voltage, multiplication of voltage and current, which is both varies due to temperature. So the PV module dimension shall include outer frame. Example, this is the length and the width. It is common for new module come with the standard MC4. This is the MC4 connector. So this is male connector and this is the female connector. This is very convenient for intermodule connection to form a series connection. So this is the symbol. When we sketch a diagram, you can use this symbol, but when you want to draw a circuit diagram, you must use this symbol. This is like a envelope. So the cover of the envelope, this is positive polarity and this is the negative polarity. So let's go through this bypass diode. So bypass diode can minimize or eliminate the formation of hotspot. If the cell module is defective or shaded, the polarity is reversed, causing the diode to conduct shunt any current flow. Some manufacturers provide a bypass diode across a string of 18 modules. In example, the module has 2 diodes with a total of 36 cells. In series connection, each module should have at least one bypass diode fitted. So this is how the bypass diode looks like. So in this figure, it has 4 bypass diodes. Okay. So for each PV manufacturer, they need to have at least one bypass diode for a small PV module. So in this figure, we have 3 bypass diode. So for one string, example here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 18 solar cells in series with one bypass diode. Another 18 solar cell with another one bypass diode. And another 18 series solar cell with one bypass diode. So total 3 bypass diode. So this is a negative polarity. And here is the positive polarity. So the current will flow from negative to positive. Okay. So how to draw the circuit diagram with bypass diode? So this is how you draw. This is the symbol of the PV module and here is the bypass diode. For one module, one bypass diode. Although the symbol shown only one diode, so most of the PV module are equipped with more than one diode. For example, 60 cell PV module is equipped with 3 bypass diode. This is example. So one bypass diode, we cater 20 cells of PV module. So in this case of 40 bypass diode, so it can be replaced by the following rating. So you need to calculate the rating before you buy the bypass diode. So the rating, the voltage rating of the bypass diode should be greater than 2 times of the open circuit voltage of the PV module. This one you can get from the datasheet of the PV module. And the current rating of the PV module should be greater than 1.3 multiplied with short circuit current of the PV module. So this bypass diode is located in what we call, this is a J box, junction box, which is located under the PV module. So this is the cable or connector for male and female MC4. So let's say we have shaded area on these cells. So when the current flow, it can't go through this cell. So it will bypass through this diode to the next series of solar cell. And then flow to the next series of solar cell. So this string is not working because of this shading. Okay. Let's say we have the whole shading here in this area. Okay, so that means the PV module is totally not working because it will bypass all the string, go through the bypass diode. So this orientation we call lengthwise up, because the lengthwise is going up. Okay. So that's all for chapter number 3. So if you have any question, you can ask through openlearning.com or you can WhatsApp me. Okay, thank you very much.